Okay, it's 8:10 now, and let's start the module 8, which is about the analysis of kinematically indeterminate frames. This should be kinematically indeterminate frames using stiffness method. We already discussed the analysis of beams, kinematically indeterminate beams by using the stiffness method. And the stiffness method, again, today we will apply it to the analysis of the kinematically indeterminate frames. Topics to be covered in today's lecture will be introduction, prerequisites for using stiffness method, types of frames, stepwise procedure of stiffness method for frame analysis, analysis of non-sway frames, and with this we will solve example 1, 2, 3, and 4 also. So till this bullet we will cover in today's lecture, and assignment obviously 4 will be also part of this today's lecture. And next week, inshallah, we will go through analysis of sway frames using by using example 1, 2, and 3, and then we will have the B part of assignment number 4. Now these types of frames, so the types of frames we will be discussing in terms of the sway and non-sway frame. What is a sway frame and what is a non-sway frame? We'll discuss them with examples. But before going to that, let's now go to the introduction part. Why stiffness method is used? Because again, because of the 3 reasons. It is systematic method. You can write your simultaneous equations, then you can put them in the standard matrix form. Matrices you can solve very easily with the help of the computers. Now, the unknowns are the joint displacements. Once the joint displacements are known by using this matrix approach, then the support reactions you can find out, and you can find out the member and actions also, which in case of the frames is axial action, shear, and the moment. Now, the prerequisites for analysis with stiffness method, as we discussed in case of the beams, you must be knowing enough concept of matrix algebra, must be able to find the kinematic indeterminacy of the frame, and you must know the formulas and concepts of fixed end actions for some standard cases. Now, coming to the types of frames on the basis of lateral displacement. Now, you see here lateral displacement. Frames are classified into following 2 types. First is frames with sways. Sway means it can deflect, can have lateral displacement. And frame without sway, it does not have lateral displacement. Now remember, one is buckling, which is the local phenomena of a member. The lateral instability, the member buckles or it displaces laterally, and it is always because of slenderness when the member is thin. So when you put more axial load, what will go? It will bulge sidewise. But in case of the sway, frame as a whole at that level moves laterally. It has lateral displacement. So one is frame with sway and one is without sway. And without sway always we call non-sway frame also. Non-sway frame means it does not have lateral displacement. While frames with sway, it has lateral displacement. Now sway frame, then now statically or kinematically indeterminate structures the frames deflect laterally due to presence of lateral loads. What can be the reason of this lateral displacement now? One can be the presence of the lateral loads. Our lateral load will not be there, but it will be having unsymmetrical vertical loads. Because of the unsymmetry, the loads will be eccentric. Because of the eccentricity, it is going to go and displace sidewise. Or where the frame themselves are unsymmetrical, or the geometry of the frame will be unsymmetrical. So causes of side sway are unsymmetrical loading, means eccentric loading. Different end conditions of the column. We have a frame, two columns and one beam. At one end, we have this hinge support. At other, we have a fixed support. So it is unsymmetrical regarding the support condition. What will happen? Chances are there that it will have lateral displacement. So different end conditions you will be looking for. You will be looking for the symmetry of the loading. If it is unsymmetrical, then there will be side sway. Third reason can be non-uniform sections of the members. One column, let's say it is having I, the other column is having 2I. Again, it is unsymmetry. So if the geometry is unsymmetrical, there are chances of the side sway. Horizontal loading on column of the frame. Horizontal loading will cause displacement. And then settlement of the supports, unequal settlements of the support of the frame. So these are 5 causes which you should be looking in a structure. And by feeling, remember, by feeling you can even find out whether this frame is going to have a side sway or it is going to be without side sway. Now coming to the examples now, here you can see frames with outside sway, means non-sway frames, which does not have lateral displacement. Now at the top left, we are looking at the frame. At the bottom, we have joint A, then above it, we have joint B, and then to the right, we have joint C. Joint A is a hinge connection, joint B is a rigid joint, and joint C is again a hinge support. A hinge support and C is a hinge support. Now, if you look at it is a non-symmetrical frame. But if you look at the support conditions, C can take vertical as well as it can take horizontal reaction. Similarly, A can take vertical and as well as horizontal reaction. So it means there are no chances of the lateral displacement. At C, you have a reaction in the horizontal direction. It is not going to allow the horizontal displacement. So when there is no horizontal displacement, it means it is a non-sway frame. We are not looking at the loads now. We are not looking at the geometry, just support conditions. It is giving you enough now condition to declare this frame as a frame with outside sway or a non-sway frame. Now coming to the right, now why this we declare a non-sway frame? The reason is, again, if you see at A, we have a hinge connection, means can take horizontal as well as vertical. And similarly, we have the conditions at E and D also. So again, it is not, although the loading is unsymmetrical, the frame is also unsymmetrical, but now the support conditions are such that they are not allowing any horizontal displacement. So it means it is a non-side sway. At A, we convert this now into a roller support. So if we convert this A instead of the hinge support into a roller support, what will happen? It is now unsymmetrical. If you look at the loading, so it is unsymmetrical. So what will happen? Then there are chances of that it can now displace, it can have displacement in the horizontal direction. Coming to this bottom one now figure, which is having 18 kilonewton pointed loads. Now, if we look at the configuration of this frame now, at A, we have a hinge support, at B, rigid joint, at C, rigid joint, and at D, we have a hinge support now. And the 18 kilonewton and 18 kilonewton, they are provided at third point now, 4 meter, 4 meter, 4 meter, if you see, so equally divided into 3 portions. Loading is symmetrical, support conditions are symmetrical, and if you see, AB is exactly same as CD member. So the geometry is also symmetrical. Now in this case, again, it is a non-side sway frame. What will happen now if we make this loading unsymmetrical? Let's this 118 kilonewton, I'm just moving to the left now. This 18 kilonewton, one of them I'm putting at the middle now, and one is at 1/3, this 4 meters. So what will happen? The loading condition will become unsymmetrical, and because of the unsymmetrical condition, what will happen? This will become a side sway frame. It will be having a side sway, then because of the loading unsymmetry. Although the geometry, the support conditions, each and everything, they are symmetrical, but the loading is unsymmetrical, and there is nothing at the BC level to stop the lateral displacement. So we declare then, and in that case we can declare, because of the unsymmetrical loading, we can declare this as a side sway frame. Again, now let's say loading is symmetrical, but the CD is not similar to that AB now. So what will happen? Because of the unsymmetrical geometry, again, this will become a side sway frame. Let's, instead of this, now each and everything is the same now, but at D, what we are doing, we are making this as a horizontal support, I mean a roller support. So what will happen? Because of the unsymmetry of the loading, chances are there that it will become a side sway frame. But in this condition where you have a perfect now symmetry in the geometry and symmetrical loading also, no lateral. Again, if it is symmetrical, this one, but if we apply, let's say at joint B, a horizontal load now, so what will happen? Again, it will become a side sway frame. It will be having lateral displacement. Coming now to this last one, which is the bottom right now corner. If we look at, we have the horizontal load now for KIP. If you look at member AB, the vertical member at the center, we have rightward directed 4 KIP load now. If I look at the load now, and if I don't consider the support conditions, so then the feeling is that it will be having lateral displacement. But if you see at side joint C now, here we have a hinge support now, which can take the horizontal load and which will not be allowing the lateral displacement. So that is why we declare this frame, looking at support conditions, we declare this as a non-sway frame with outside sway frame. Although it is having the lateral force now, but C can take and this A can take also the horizontal forces. So we declare this as a with outside sway frame. Now, instead of this hinge support at C, if we now replace this by a roller support, then what will happen? It will not be having the capacity to stop the lateral movement now. So what will happen? This will become a side sway frame in that case. Now, some of the examples from with side sway frames. If we look at the first one diagram where A, B, C, D joints are shown, and this pointed load, which is 1 meter from the left, from this left joint and 3 meters from the right joint, means it is unsymmetrical now. Looking other conditions now, at the top, we don't have any arrangement to stop the lateral displacement. A and B are similar, both are hinge support. So what will happen? Now, the frame is symmetrical, but the loading is unsymmetrical now. So what will happen? It is going to deflect sidewise. It will have lateral displacement. How it is going to display this have lateral displacement? This AD will come to the right, and then BC will also come to the right. So at the top you will have this displacement. And remember, displacement at the same level is going to be same. Means whatever displacement you have at D to the right, the same displacement you will have at C to the right. If it is to the left, so at both it will be to the left and by the same amount. So here now, in this case, the lateral displacement is because of the unsymmetrical loading. Coming to the right top one diagram, A, D, C, and B, we have the frame now. At A we have, so, and at B the same level and same, so this is symmetrical. But if you look at AD is not similar to the BC member. Again, we have lateral loading also. Again, at B, C, and D, we don't have anything to prevent the lateral displacement. So clearly now this is a side sway frame. Now bottom left one, AB, again we have the supports, hinge supports we have. But if we look at the at AD, we have lateral load now 0.2 kip per foot. At DC level, we don't have any constraint now in the horizontal direction. So what will happen? It is going to go sidewise. And again, if you see the left vertical member, which is AD, it is not similar to the BC member, to the right member, which is 12 feet. So again, clearly just by observation, you can see it is a side sway frame. Now, the last diagram now, again, at AD we have now supports, and BC, the top one, it's a symmetrical supports conditions, the members, each and everything is symmetrical, but it is having a lateral load now, which is 8 kip at C leftward directed. And at BC level, we don't have any constraint in the horizontal direction. So what will happen? It is going to deflect to the left side now. And because of that displacement, it is declared as side sway frame. So in today's now lecture, we will be discussing the analysis of the frames with outside sway or non-sway frames. So part one, which will be the discussion today, it will be analysis of frame with outside sway. And remember, it is the simple case. The next one is going to be a little bit complicated. Complications in terms of when you have displacement, so it means additional kinematic indeterminacy is coming. And because of this additional kinematic indeterminacy, the kinematic indeterminacy of the structure will be higher, more computational load, and because of more computational load, then more complexity also. So now stepwise solution procedure using stiffness method. Again, remember, the steps are exactly the same which we did in case of the beams. And how many steps we were having? We were having step number 1, and where we, based on the kinematic indeterminacy, we identify our unknown D's, and we make the AD's matrix, which is corresponding to those unknown D's. So D's, we declare them unknown, their direction and their location we fix, and then corresponding to those, we look for the externally applied actions and we include them as a AD matrix. So AD matrix is constructed in first step. Step number 2, what we were doing, we were constructing the ADL matrix. And what was ADL matrix? Those were the fixed end actions corresponding to the unknown giant displacements and the restraint structure. So step number 2 was about the ADL matrix formation. What was step number 3 now? It was the construction of the stiffness coefficient matrix. And how we make them? We make this stiffness coefficient matrix by applying the unknown joint displacement turn by turn. We allow rotation at that particular point, and we restrain, or we do not allow the displacement at other locations. So when we apply at location 1, first column of the stiffness matrix is generated. When we apply this displacement at point 2, second column of the, and so on. Now remember, in step number 2, while we are generating the ADL matrix, from there we will have to make our AML values also. From there we are going to grab our AML values. And from the diagrams from where we are making our stiffness coefficient matrices, this S matrix, I mean, so from there we will be making our AMD matrix also. So you must be remembering these things. So in these first 3 steps, we find out the parameters AD, ADL, and S. Now we are in a position now to make simultaneous equations out of these one, and the fourth parameter, which is the displacement, that is the unknown. And if you see in step number 1, already now we took that as our unknown. So this fourth quantity, which is the D, now we can find out by the solution of the equilibrium equation. So step number 4, we have reserved this for the solution of the equilibrium equation. And in step number 4, when we get the unknown displacements, then we go into step number 5, and we find out the member inductions, or we can find out the support reactions also. And then in step number 6, what we do with the help of those known member inductions and support reactions, we draw the shear force and bending moment diagrams. So step number 2, apply the actual external loads on the basic kinematic determinate structure and find the actions at the locations of redundant joints displacements. Now means compute fixed end actions corresponding to the redundant joint displacements, and this way we generate the ADL matrix. Step number 3, apply the redundant joint displacements on the basic kinematic determinate structure. And what we do as a standardized procedure, we apply only a unit displacement in the positive direction. In positive direction, we say clockwise, let's say rotation is going to be positive. And similarly, corresponding positive clockwise moments also we take positive. So that is how becoming our positive direction. If you want to take counterclockwise as positive, your choice. So correspondingly, the counterclockwise moments will also become your positive actions then. And this way we generate the stiffness coefficient matrix. Remember, from this step number 2, you will be completing your AML values, and from step number 3, you will be completing your AMD values also. Now step number 4, while we have this AD from step number 1, ADL from step number 2, and S from step number 3, now the only unknown is now this D now. So we rearrange this equilibrium equation in terms of this unknown D, and this is becoming now S inverse AD minus ADL. We have all this right hand side, all these 3 parameters, so we can put them in the equation and find out the unknown D's now. Compute the member end actions. So for the member end actions, what is the equation? AM is equal to AML plus AMD times D now, and D already we found here. And after this, then we go and we draw the shear force and bending moment diagrams. Now, with this much lecture now, let me ask you that now you can interrupt me and you can start asking me questions. Mr. Sajjad, do you have any question?
No, sir, it's clear, sir.
Clear? Okay. Mr. Anas. Anas Alam, are you there? Mr. Jawad Ahmed. Do you have any question? Is your microphone on? Because I cannot hear you, Mr. Jawad. Mr. Sofyan.
Yes, sir.
So, do you have any question?
No, sir.
Okay, so let's proceed now. If you don't have any question, that is good. Then let's now proceed. Now we are coming to the actual frame. So now, if you want to take 2 minutes, you can take 2 minutes. You just bring in your pen, your notebook, and your calculators. Now, if you want to verify some numbers, we can verify. Problem number 1, we will be going very carefully now, and then 2, 3, and 4, we will be running quickly over problem number 2, 3, and 4. So in problem number 1, if you want to verify things, you should be sitting with your pen and notebook and calculator. So just take 2 minutes, bring them in, and then I'll start this problem number 1. And you make a note of this one also on the page, so that when we go now to the next slide, so that you remember which one giants we are discussing, which one supports we are discussing, which one members we are discussing. All these things you should be having on your sketch. Okay, so let's now start this frame now. It says analyze the given frame using stiffness method. The configuration of the frame now, at the bottom we have A support which is fixed. Now above this A we have B joint which is a rigid joint, can resist the moment. It's also known as a moment joint. And just to the right of this B now we have C, where we have a hinge support now. So BC, it's a beam now, if you see, horizontal member, and AB, it's a column. AB height is 10 feet and BC is 12 feet, written here 12 feet, and this is the 10 feet. Take EI is equal to constant. So EI property is given, that constant for both members. If they are given now in some numbers, or let's say they are different, so you will have to take them accordingly. Coming to the kinematic indeterminacy. Why kinematic indeterminacy? Because we are dealing with the stiffness method. So the first requirement of the stiffness method, you must be clear about the kinematic indeterminacy. What is kinematic indeterminacy and how we find it for a structure. Now, simply, if I start now finding out the total kinematic indeterminacy of this problem, So how can I do it? We have 3 joints, and let's say these 3 joints were free. So each joint can allow 3 displacements now. So 3 times 3 is equal to 9 degrees. It was kinematically indeterminate to 9 degrees. But now we have constraints. Out of those 9, now we need to subtract those constraints now. So at A, we have 3 constraints: vertical, horizontal, and then moment also. And at C, we have 2 constraints: vertical and horizontal reactions. So we got 5 constraints now. So this structure is now in this shape. If we take it now according to these supports, members, and each and everything, so it's 9 minus 5 is equal to 4 degrees kinematically indeterminate problem. But now as it is a bending dominated structure, so we can neglect the axial effects now. And if we neglect the axial effects, means this BC is not allowing any lateral this displacement, and AB, the vertical, is not allowing any vertical displacement. So horizontal and vertical both are not allowed. So it means we can take out now 2 displacements out of these 4 displacements. So it means it is becoming kinematically indeterminate to 2 degrees. And what are those 2 degrees now? It is just a rotation at this joint B, and it is rotation at this joint C. So at the bottom now you see this kinematic indeterminacy 2 degrees, and when 2 degrees, when we neglect the axial effects. If we take these axial effects, then it is a 4 degrees indeterminacy. Now, so now 2 redundant joint displacements should be chosen, and what will be those 2 unknowns? It will be theta at B and theta at C. But we will make a general notation for this, and instead of thetas and deltas, what we do, we write them in terms of the D's now. So next slide, if we go now, so here now we identify our unknown joint displacements now. So step number 1 is selection of redundant joint displacement. Redundant joint displacement means the unknown joint displacements, and assign coordinates to those locations. Also compute AD values. When you give them their labels, then you are in a position to make your AD corresponding AD matrix also. So now rotation at B, which is unknown, I am declaring that as D1, and rotation at C, we are now labeling this as D2. So rotation at B and C are taken as redundant joint displacements. I'll be with you in a second. I've got a phone call. Hello. Assalamu alaikum. ना जो लेक्चर के मसल के ऑनलाइन लेक्चर के ना माता बिल्कुल रागला खुशो बल ग्लेट राजा मसल के ज़माने डेर कारुना दिया पक्की देश सबा सार वक्ती बैर राजा ठीक शो हाँ نو تاسو بس ټیم پورې زه بس ټیک ته زه به کوشش کوم چې 3-4 بجو مې سکو راشم زه به کوشش کوم خو کنه نو خیر لږ نا وخت د ما کارونه دي ټیک شو زه صحیح نه راځم خو راځم ان شاء الله خدا سي 3 بجو پوښتنه السلام علیکم Okay, so now D1 and D2, and you see the sense also clockwise and clockwise. We say the clockwise rotation. We assume that initially that it is our positive direction. Now in the actual structure corresponding to D1 FVC, we don't have any externally applied moment now. So we take AD1 is equal to 0. Similarly, corresponding to CFUC, we don't have any externally applied this moment, so it means it is also 0. So we declare this AD2 also is equal to 0. D1, D2 we have labeled, and then corresponding AD1, AD2, and we have constructed this AD matrix. Step number 2 now. For step number 2, first what we do, we make the structure kinematically determinate, which is known as restraint structure. So here you can see restraint structure. At B, what we are doing, we are putting a fixed support. You can put, obviously, you can put it in the vertical, so it's fine. This is just to make it visible. I put this in the inclined position. And then at C also, you put this fixed support. It's now a restraint structure. Why restraint? Because none of the joints is allowing any kind of displacement. Next, now we come to step number 2. Now, after getting this restraint structure, we load it with the actual load. So restraint structure acted upon by the actual loads, and we find out the member and actions. Remember, if I was interested only in the ADL matrix, so what were the numbers which we should be finding? We should be finding the moment now at this joint B and the moment at this joint B now because of these externally applied loads. That will give me my ADL matrix and the moment at C. Now only these 3 numbers were required. But now why I'm going in such a detail now, all the member and actions we are finding out. Why? Because rest we are going to use when we go to the AML matrix. So that is why here clearly I am writing all the member and actions. Now coming here to this vertical member, which is AB, if you see, we don't have any lateral loading on this one. So what happens now? The member end moment is equal to 0. Why? Moment is always load times distance. So if we don't have load, so it means we don't have any moment. There is no moment and there is no shear force also. Nothing is going to be balanced by these shear forces. Now this 12 and 12 is coming from where? We need to look for these numbers now, because this member was not having any force, but now axial forces we have 12 kip. So from where those are coming, we will discuss this in a while. Coming to the BC member now, 2 kip was per foot was the load intensity, UDL, and then 12 feet is the distance now. So the member end moment, because of this, the fixed end moment is WL square divided by 12, so it is equal to 24. On the right side also 24. We don't have any unbalanced moment, so half of the load will go to the right support and half of the load is going to go to the left support. So 12 times 2 is 24, divided by 2 is 12 kip. This is how we are getting 12 kip. You can verify this WL square divided by 12. This will become 2 times 12 square divided by 12. 112 is going to cancel with this 112 and 2 times 12 become 24. So already it is verified now. Now remember, this 24 kip moment, we are not transferring it to the AB. Why? Because we have restrained this rotation here. And how can you restrain this rotation? While still it can slide in the vertical direction, it can slide in the horizontal direction also. Only rotation was stopped, D1 was stopped here. So now when it can slide in the vertical direction, it means this 12 kip, when it starts sliding in the vertical direction, it is going to be taken or it is going to be transferred to this BA member. And this joint must be in equilibrium. So this 12 kip, it can transfer to this B joint here. It's the same joint B. Because of that sliding, because that is still permissible here, we have stopped only D1, which was rotation. So this 12 kip is in the upward direction. Here it is going to be in the downward direction. This joint is in equilibrium. Now at A already we have a support now. So what will happen? This 12 is going to be balanced by this 12 cap now. So this is how this 12 cap is now moving to this support A. And we see now the joint is in equilibrium as well as the member is also in equilibrium. Now remember, if there was some shear force in B now in the horizontal direction, so this we did not stop the horizontal sliding here. So what will happen from this joint B in the opposite direction, it will shift to joint B of the BC member, and from BC, for BC member, it is going to be balanced here by this joint C force. Now, so here you will have the opposite reaction, whatever you have on this B. So the member has to be in equilibrium. So maybe in the next problem, we are going to have this kind of situation. Now, coming to the ADL matrix. Now, ADL matrix, if ADL1 we are discussing, so we are coming to now this coordinate 1 now. This is the D1 location now, which was joint B. And the corresponding actions to the rotations are moments now. So from BA, MBA is how much? It is 0 now. So 0, and this if we see from BC, this MBC is minus 24. Now why minus? It is counterclockwise movement now. So 0 minus 24, which is minus 24, and here it is recorded ADL1 is equal to minus 24. So this is coming minus 24. Now to find out this ADL2, we are coming to the D2 location. At D2, if you look at this moment, corresponding moment which is corresponding to D2 now, it is in the clockwise direction, means positive. So plus 24, it is now our ADL2 now. So ADL1 and ADL2 values you have, one is minus 24, one is plus 24. Let's at B, we were having, let's say 4 kip feet now, and it was in the clockwise direction. This was the direction clockwise. So in that case, we have plus 4 minus 24. So the result will be minus 20 then. 4 minus 24, 20. So you will have to take the algebraical sum and the appropriate sign, whatever the end sign you get, you will have to put that sign also along with the magnitude. So that easily now you can find out your ADL1 and ADL2. So after this, we go to the stiffness now method. So what we do in the stiffness method now, so primary structure, not primary structure, it is the constraint structure. So let me now, the restraint structure, I mean, so it is the restraint structure is acted upon by a unit value of D now, and computation of stiffness coefficient values in the basic kinematic determinant structure corresponding to the redundant joint locations. And how we proceed now in this case, if you see now, first a unit rotation. Why unit rotation? Because rotation was the unknown in this case. If the translations are unknown, then you will have to apply a unit translation. So first a unit rotation is applied at location 1 and prevented at other locations. In this case, only we have location 2 because it is 2 degrees kinematically indeterminate. And this way we compute the first column of the stiffness matrix, and its elements will be S11 and S21. S at 1 due to 1 and S at 2 due to 1. Why? Because at one location we have applied the unit displacement. And then it is followed by the application of the unit displacement corresponding to location 2. And what we do for rest of the location, we keep them locked. And this way we generate the second column, which elements will be S12 and S22. Now let's demonstrate now these two steps for the 2 steps of step number 3 for this particular problem. If you see now, we have that A, B, and C. At A, what we are doing now, we are providing that unit rotation. So you can see theta is equal to 1 and theta is equal to 1. Why this deflected shape? Why not the other way around? This bulging is going up. Now, instead of this concave, we have convex here. And this is now to the right we have. So what will happen when you start tangent now to that new deflected shape? What will happen from the initial stage if we start and if we move this cursor? So it means it is because of the counterclockwise rotation, which is against our now assumption. Our assumption was clockwise direction was positive. So here you can see to the deflected shape for this beam, if we draw this green line as a tangent, it is a clockwise direction. Similarly, for the vertical member, this deflected shape at B, if we draw a tangent, this green line you can see. So again, it is a clockwise direction now, clockwise and clockwise for both one. So this is according to our assumption. Now, if you see these original members which are shown in red lines, the straight lines, this vertical and this horizontal making a 90 degrees. But if for the deflected shape now, if you see again these green tangents, again they are making 90 degrees with each other. And this is the property of the rigid joint now, that it rotates by the same amount. Now at B joint, we are providing this rotation already for the rotation and the member and action, which is a moment. We have a very nice relation at the near end, 4EI over L, 4EI theta over L, but theta in our case is 1. So we just disregard that number. We don't show it while we are writing at the far end half of that amount. Similarly, here you can see, and the sense of this moment again is going to be the same as that of the rotation. So 4EI over 12Y12, because BC member is 12 feet, here it is written. Far end, it is 2EI over 12, half of this one. Then the balancing couple now. So the balancing couple, the unbalanced couple is in the clockwise direction. So the balancing couple will be in the counterclockwise direction. So here we have a downward now reaction of 6EI over 12 square, which is not shown here because then we have a lot of numbers and that will cause now congestion, and because of congestion then you will get confused. Coming to now the vertical member. So because of this rotation at B now, for the vertical member at the near end we have 4EI theta over L, so it becomes 4EI over 10 now. 10 is the length of the member now. At the far end now 2EI over 10. Now it is causing again clockwise movement. The unbalanced movement is clockwise, so the balancing moment should be counterclockwise and it should be 6EI over L square. So here you see 6EI over 10 square, and at the bottom you see their directions also. Again, now coming to the which one actions we can take to the end supports now. So here, if you remember, it was downward 6EI over 12 square, the couple, this one couple I'm talking about. So when it is downward, so at B joint for member AB, it will become in the upward direction now. And we have a support here, so here it is going to be balanced by this downward. So 6EI over 12 square, this is how we get this axial force and member AB. Coming to BC member now, here the shear from this AB member, it is leftward directed CEI over 10 square to the leftward. At the same joint B for member BC, it will become rightward directed now 6EI over 10 square, which is going to be balanced by the leftward directed 6EI over 12 square. So it means that if we take this, this one along this number, so I should be showing it to the right now here 6EI over 10 square. So when you get to the AMD's matrices, you should be taking these values accordingly. Now from here, we will make the first column of the stiffness matrix as well as the first column of the AMD matrix. Now, let's talk about the first column of the stiffness matrix. So stiffness matrix now corresponding to D1 now, we should be looking for the moments now. So we have a clockwise moment now 4EI over 12, and we have a clockwise moment of 4EI over 10. So the algebraic sum of these is going to make your S11 value 4EI over 10 and plus 4EI over 12. So you should be making a note of this, that S11, because after this I'll be switching to the next slide. So our S11 is equal to 4EI over 10 plus 4EI over 12, corresponding to D1, these moments I'm taking. S21 will be equal to, this is 2 location, and because of 1 rotation we are getting this action, and it will be equal to now this 2EI over 12, and again it is clockwise, so it is a positive value. So this is 2EI over 12, and you can confirm here now 4EI over 12 plus 4EI over 10, and S21 is equal to 2EI over 12, and here now we have these values in the decimals. So 0.733 EI and S21 is 0.1667 EI. Now, second part of this step number 3 will be, now we will give a unit rotation at point 2 now. D2 is equal to 1 we will put, and D1 we will put equal to 0. And here you see their situation. Here we are applying now rotation. So this orange line, let's to the right, now we make it inclined, means we give a rotation. What will be the deflected shape of this beam? This will become the deflected shape. Here we are not allowing any rotation now. If we draw a tangent here, so here you see to the tangent, this is making a clockwise now, theta is equal to 1 now. This is becoming our now near end, and this is the far end now. So at near end, the moment generated will be 4EI over 4EI theta over L, which is 4EI over 12 in this case. At the far end, 2EI, and the balancing couple again here downward. Why downward? Because the unbalanced couple was clockwise, so the balanced couple should be counterclockwise. So this should be down, and this should be upward direction. So 6EI over 6EI theta over L square. These are becoming the reactions. Now you can see here, it is not going to allow this rotation to the BA member. In BA member, we don't have any kind of activities in terms of the displacement. So the corresponding moment is 0. And the shear forces are also 0. From where this 6EI over 12 square is coming, it is coming from this vertical reaction now. From member BC. It was downward. At B, it will become upward, and then it is going to be balanced by this downward 6EI over 12 square. Here, what will be the horizontal force? We don't have any horizontal force here from member AB, so that 0 is going to travel here. So it means horizontal here is equal to 0. Coming to the stiffness matrix now. Now, S at 1 due to 2, S12 will be equal to, from member BA we have 0 moment, but from member BC we have 2EI over 12 now. So 0 plus 2EI over 12. So S11 is equal, S12 is equal to 2EI over 12. You make a note of this. S12 is equal to 2EI over 12. And S22 is equal to 4EI over 12. Although we have other member end actions also here, if you see, but the corresponding one is this moment now, which is corresponding to D2, and it is in the same direction. So this is how we take its sign, and this is how we take its magnitude. So 4EI over 12 is our S22, and here you see them clearly. S12 is 2EI over 12, must be equal to S21, and S22 is equal to 4EI over 12, and then you see them in the decimal form. Now with this, now we are in a position to write this matrix in a very nice form. EI is common, so we take that as common. It's from here 0.733, 0.1667, 0.1667, and this is 0.33, and this is our stiffness matrix now. AD matrix we have, ADL matrix we have, and we have the stiffness matrix also. And this is now our simultaneous equations. This is the standard form in the matrix form. This is the condensed form of the equilibrium equation, and this is the rearrangement in terms of the D now of the equilibrium equation. We plug in the values here. It was EI, so inverse when we take it becomes 1 over EI. Here we need to take the actual inverse of this stiffness matrix. 0 and 0, if you remember, AD1 and AD2. Now ADL1 was minus 24. So here you see minus 24. ADL2 was plus 24. So you see here plus 24 now. When we solve this, so D1, D2 is coming out equal to 55.40 and minus 99.742. Here now you see D2, we assume that in the clockwise direction. But here when we find out the displacement at D2, it is coming in the counterclockwise direction. And you can see it from the diagram also. If we go back to the diagram, so what will happen if we go to the original one? This is the original one. How this beam is going to deflect? This is going to deflect this one, concave shape here at near this support, see, because of this loading. So now if we draw a tangent and if we draw now a curve now starting from the original position to the deflected position. So you see here how this actual rotation is going to be. It is going to be counterclockwise. That is why our initial assumption, which was this way, which was convex near this C, that is wrong now, because that was because of the clockwise. So from here now you can check the flexibility also, that initially how much you are now, there is flexibility to assume your direction. Finally, what will happen at the most? If it is wrong, you end up with the negative sign. So this gives you the sense of the deflected shape, also how the deflected shape of the this frame will be looking. So D1 and D2 are known now. Now we can go in step number 5 and find out the member and actions. So how we are going to do that? We now go member by member now. We select this member AB, which is the vertical member. And we designate initially our AM's member actions now. What is my assumption now? I assume upward, rightward, and clockwise as my positive direction. Upward, rightward, and clockwise are my positive values. And I'm coming to a specific end now. Let's say this A is my near end, starting end, let's say. A is starting end, so vertical followed by horizontal followed by the moment. This is my labeling sequence now. AM1, AM2, AM3. First, I assume my positive directions, upward, rightward, and clockwise direction. Then I designate a starting end, let's say is my starting end, and then I start labeling. So let's upward followed by rightward followed by the moment. That is my labeling sequence now. So then I go to the far end, again upward, rightward, and you see the moment, which is clockwise direction. So AM1, 2, 3, 4, 5, 6. Remember, in this sequence now, we are bound after this to follow the same sequence for the AMLs and for the AMDs also. You can start this from the horizontal adjoint A. Let's say this is your AM1, this is AM2, this is AM3, or you can start from the moment also. But then that sequence has to be followed for the AMLs and for the AMDs also. Now, AMLs, from where we are going to pick our AML values, we are going to pick those from where we generated our ADL values, which was restraint structure under the actual loads. And remember what was there? This 12 and this 12 cup we discussed this was coming from the horizontal member. This is the same situation. Now the same, you don't need to redraw again this one. You just show that these are my A, M, 1, 2, 3, 4, 5, 6, because 6 member and actions are in a member. At each joint we have 3 actions: axial, shear, and moment. And similarly at the other joint we have the same 3 kinds of actions. And straight away now you start making your AML matrix. Now this is just to show you. So now you see this AML1 is exactly pointing to the AM1 location, AML2 corresponding to AM2, and this is corresponding to AM3. Now AML1 is how much? This direction already we found with the help of the applied loads, and it is same as our positive direction. So AML1 is becoming equal to 12, which is shown here in the matrix. AML2 we don't have any horizontal, so it is 0. AML3 we don't have any, so it is 0. AML4, it is in the downward direction now, opposite to this positive direction. So it means this 12 we need to put this with the negative sign now, because this is not matching to our assumed positive direction. AML4 now minus 12 you see. AML5, it is this horizontal, which is 0. AML6, it is 0. So that quickly and easily we can find out our AML matrix for this member AB. Coming to the AMD now, for this member we need to make now our AMD matrix. Now again we are taking member AB, but now we are taking from where we generated the first column of the stiffness matrix, and how that was constructed. Again at location 1 we applied the unit rotation, and you see that thing here at location 1 you see theta, all these member and actions. Now you can see again where is the reference for these designations. The reference is again where we selected our AMs. So AMs, that is your reference now. So AMD 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, and 6, 1. Corresponding values now you need to pick from here. So quickly now you write down AMD 1, 1 is equal to minus 6 EI over 12 square. AMD 2, 1 is equal to, it is in the same direction, 6 EI over 12 square. AMD 3, 1 is equal to 2 EI over 10. AMD 4, 1 will be equal to, here it is in the upward direction, the same one, 6 EI over 12 square. AMD 5, 1, here if you see it is 6 EI over 12 square, and AMD 6, 1, this moment 4 EI over 10. So this will give you the first column of the AMD matrix. Second column is going to be generated from here, where we completed the second column of the stiffness matrix. Now again, this vertical member we are concerned with. So AMD 1, 2, 2, 2, again the reference for this labeling is again the AMs which we did. So AM12 is how much? It is minus 6 EI over 12 square. AMD22, it is 0 here. AMD32 again 0. AMD42, so it is in the same upward direction here, this reaction. It is in the upward direction. From where it is coming, it is actually coming from BC. Here it was downward, so at B for giant AB, it is in the upward direction. And similarly, A62, it is equal to 0. And this way now we have completed this AMD matrix. Now we have AML values, we have AMD values, we have D values also. So we can put this in this equation form. Look, with the actual signs, you will have to put those D's, the unknown D's. Remember, this was 55.40 minus 99, and it was 1 divided by EI. And these values are EI times these values. So EI times 1 over EI, they will cancel each other. And we are left with these solid numbers now. So product of these two matrices plus addition with this one, and these values we get now. AM1 now here, it is upward directed 13.8. AM2 at joint A, it is rightward directed 3.3. AM3, it is clockwise 11.1 movement at joint A. Coming to joint B now, so it is downward 13.8 now. AM5 it is leftward directed 3.3 now, and AM6 it is clockwise 22.2, and we put them on the sketch now. Look, corresponding to these labels now we put all these values, and you can see this is analyzed member now. In AB member now, how we draw for this AB member the shear force and bending moment diagram. We show the external loads also on this member AB. We have the member and actions. For member AB, we don't have any external action. So it's very straightforward now to draw its shear force and bending moment diagram. 3.3. So we are coming to the right because of this 3.3 shear. We don't have any load in between, so it is becoming constant. 3.3, the same magnitude here we have. And because of this 3.3, we are coming to the left. So we got this closed loop now. Because of this 11.11, we are coming to the left. And because of this 22.2, we are coming to the right. This is 0 degree. It should be 1 degree. We are joining these points, and this is becoming the bending moment diagram for member AB. The same process we are going to repeat for member BC also. So let's go to member BC now. Here, now you see the member and actions designations now. B, let's say it is the starting end, and C, it is the ending end now. So horizontal AM1, again, if you see rightward, upward, and clockwise, rightward, upward, and clockwise, we are taking positive, these member and actions. If somebody asks you that already we found this AM1, 2, and 3 for member AB, for whatever actions, member and actions we have at B now for member AB, that is going to be the same magnitude for BC member at joint B, but in the opposite direction. So why we are finding that person is right? We don't need to find this again. But let's, from the start, you are starting from member BC. So in that case, you will have to find out these values, or you can use these values, these joint B actions, as your verification, whatever you did for member AB. So that will verify those values. So now you make a quick now labels of these member and actions for member BC. Now AML values we will be taking now. So AML values for member BC, you see here, we are going to the ADL now, from where we generated our ADL matrix. So we are going here. These are those member and actions now. AML1 is how much? Corresponding to this, we don't have any horizontal action. So this is 0. AML2, this is this 12. So we are putting 12. AML3, it is clockwise positive, but actual one is 24. So this is minus 24, opposite to this positive direction. AML4, it is 0 here. When number is not shown, it means it is 0. AML5, it is plus 12, so plus 12 is here, and AML6, it is clockwise positive, means so plus 24 we are recording here. Now AMD matrix we go. So AMD matrix, again now these labels are corresponding to those AM labels which we did for member BC. And we are concerned with these values now. So AMD11 will be how much? It will be this 6EI 12 square. But here we have shown this for member AB. So for member BC, it will become rightward directed. Rightward directed means it will be with the positive sign. Why? Because we are discussing the BC member. AMD21 will be this downward couple now, the other now force of this 6EI over 12, which was in downward. So this will become minus 6EI over 12 square. You should be making a note of this one also, that AMD21 is equal to minus 6EI over 12 square. AMD32, so it is 4EI over 12. AMD41, it was rightward, so here it is going to be leftward, so this will become minus 6EI over 12 square. AMD51, it is plus 6EI over 12 square. AMD 61, it is 2EI over 12. So first column of the AMD matrix is formed. And again, remember, it is the same sketch which we used for the generation of the first column of the stiffness matrix. Next, now, the second column of the AMD, again, you look at the number. And from here now, we are going to take our AMD 1, 2, 2, 2, 3, 2, and so on. So AMD 1, 2, here we don't have any horizontal, so 0. AMD 2, 2, it will be minus 6EI over 12 square, this vertical reaction. AMD 3, 2 is 2EI over 12. AMD 4, 2, it is 0, we don't have any. AMD 5, 2, it is 6EI over 12 square, and AMD 6, 2, it is clockwise 4EI over 12. So this is now we have made this, and you can verify these values. You have noticed them in terms of the 6 over 12 square and such kind of numbers. Now you run the calculations and verify 1, 2 values. And if you have any questions, so before the break, you can ask me the questions. Now, after this, we write this in the equation form. AML we have AMD, we have D also. And this way we find out all the member and actions now. These member and actions now we put them on the sketch. Now, so here now we have put all those values. If you check this joint B, it is exactly the same magnitude which we were having for BA member, but in opposite direction. So all the support reactions and member and actions note. Now we are in a position to draw the shear force and bending moment diagram for this one. So this is the routine matter now, drawing the shear force and bending moment diagram. After this, now you can go and you can combine for both members the shear force and bending moment diagram. So this is the combined shear force diagram and combined bending moment diagram, and this completes our problem number 1 for the with outside sway frames by the stiffness method. We'll be discussing this problem number 2, but that is going to be our discussion after the break. Now you can turn on your microphones and you can start asking me questions now. I'll give you 1 minute. If in 1 minute, if you don't ask me any question, then I'll assume you are clear about the topic. We can go for a break, and after the break, we will continue rest of the 3 problems. It is 9:24 now. I'll wait till 9:25. If no question is coming, I don't need to ask each and every person individually. If no question is coming, I'm assuming that you are clear about the topic. Okay, so we stop here now and we will continue. Now it is 9:25 now, so you should be back by 9:45. We have a 20 minutes break now. So you should be back by 9:45.